Tonight, we are going to witness the most anticipated match in the history of do-it-yourself blinking for a technological Christmas display in the world. In the left corner, sporting the blue and green colors, the challenger, a first-time contender, weighing in at 512 pixels, arranged in a 16 by 32 vertical matrix. 5 pixels! In the right corner, in red and white, weighing in at 512 pixels, arranged in a 16 by 32 horizontal matrix, your current champion, 12-volt Pixel! Ladies and gentlemen, are you ready? Yeah. Oh wait, I can't do that. That's copyrighted. Let's light this candle. Hi. Welcome to Canispader Christmas. All right, following up from the last video. So if you didn't see the 5-volt matrix prop build, that will show up here somewhere. Now the competition, as shown in the intro, that'll begin in a little bit. But I got a few questions asking for more video on the power injection stuff, and I will accommodate. So here's how I hook this up. So coming out of here are the wires just going into the normal pigtail of this first pixel. The first pixel is right here. And then this bottom two wires are the power injection wires, and I've injected here all the way down. And so I did it at every loop. So I went here, 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 all the way down. One of the comments I got about this was this is massive overkill for power injection. In other words, I didn't need to inject that much, and that's true. But since I'm going to be running this at 30%, I probably could have used half or less of the actual connections that I made on the bottom. So I could have skipped a loop, I could have skipped 2 loops. I actually think I have a better idea of how to approach this in the future. So how might I do this different in the future? All right, pixel number 1 is down there, so we connect that up to the power supply normally. Then run a pair of power injection wires all the way to the end and connect the end, and then see what it does. Most likely you'll have these lit up pretty well and these lit up pretty well with some darker stuff in between. So all right, then go to the midway point where the pixels are, do a power injection there and see if that fills it in. If it doesn't, then you go another halfway point and see if it fills it in there. So you're basically just working backwards. Start here, inject at the end, and then go halfway back, and then split that in half again if you need it. I'm sure I don't need every one of these loops injected. It's not going to hurt anything, it just wastes time. All right, I have a 12-volt power supply feeding the input to the right side of the F16 V3. I've got the 12-volt pixels wired up through a differential controller, so I went ahead and just used that since it was already connected up. Here's the data coming in from the computer, and then on the right hand side I have the 5-volt power supply for the 5-volt pixels feeding the 5-volt or the left side of the F16B3. Coming out of port 1, I have the wires for the pixels, the 5-volt pixels, right here. For the power injection, I have another set of wires coming off this power supply. I have this inline fuse holder on the power injection wire. Now, you might notice that the wire on this fuse holder is thinner than the power injection wire. But I have a 40 amp fuse in there. There's no way this wire is going to safely carry 40 amps. So this is basically just a piece of wire in here, and this would actually probably burn up first before the fuse. So we will be going through some calculations on wire size in a little bit, but I just wanted to show you for the demo, that's what I have connected up here, and so that's pretty much it. For the power injection, you just come off with another set of wires to feed the power injection side. But since they're not protected by a fuse like this one is, then you need to add a fuse, your own fuse in line. I've also had a few questions about wire size for power injection. So I'm going to go through a short slide presentation that will hopefully explain how to kind of figure out what you need. Now, before choosing your wire size, you need to figure out how much current the power injection wiring will be carrying. No, I will not do your math homework for you. But I will show you how I do it. This is a diagram of two sides of a standard bullet pixel. There are 3 connections. Now, there are pixels with 4 connections, but most popular ones using the WS2811 style chip have got 3. Now, one is positive, one is negative, and one is data. The input is usually marked as DI for data in. The other side of the pixel also has the same number of connections to pass power and data onto the next pixel. The data line in this case is usually marked DO for data out. These are from the pixel's perspective, so data coming into the pixel and data going out of the pixel. If you could look at the top of the pixel, maybe you've got a magnifying glass or a microscope or something like this, it might look something like this. There are 3 LEDs in each pixel, 1 red, 1 green, and 1 blue. Now, some of the newer pixels do have a white LED, but again, this is the most popular using the WS2811 style chip. For the purpose of calculating how much power each pixel uses, the typical calculation is to use 20 milliamps for each LED, and that's at full brightness. So at 100% brightness, the red LED will consume 20 milliamps. The green LED at 100% brightness will consume 20 milliamps, and the blue LED at 100% brightness will consume 20 milliamps. Now, that is rounded up for the purpose of calculating current draw. These chips can't actually draw 28 milliamps per channel, but it's close enough for our needs. So each pixel at 100% white, meaning all 3 LEDs are at maximum, draws 60 milliamps of current. Now, I say this is typical. You still need to check the specs on your pixels to figure out how much current they use. Some use less and some use more. At 100% brightness, each pixel uses about 60 milliamps. So 10 pixels would use 600 milliamps or 0.6 amps. 100 pixels would be 6 amps, and 1,000 pixels would use 60 amps. So let's cut this in half, run it at 50% brightness. So instead of 60 milliamps, now 1 pixel uses half that, or 30 milliamps. 10 pixels would be 300 milliamps, or 0.3 amps. 100 pixels would be 3 amps, and 1,000 pixels would use 30 amps. Same pixels, but now you've cut the power draw simply by cutting the brightness. And we'll talk more about that in a minute. So let's say we have a string with positive, data, and negative. Let's put some pixels on there. Here's our power supply, and we'll connect up a controller and then feed the pixels. Now this is the standard connection for short strings. What do I mean by a short string? It means any string you can run from a controller or differential receiver that doesn't need power injection. So how many is that? Well, typically for 100% brightness, you can go about 50 to 80 with 5 volt pixels and 80 to 100 with 12 volt pixels. Now, if you drop the brightness, those numbers increase because the pixels aren't using full power. So if you drop the brightness to 50%, you may be able to double those numbers. On the matrix, I ran a couple of wires off the power supply through a fuse. Start at the end of the string and just work your way back until all the lights are working. Here is a small spreadsheet for calculating current for your strings. In column 1, I have a string of 100 pixels. Column 2 is here really only for illustrative purposes, just kind of showing you what the current is going to be for 100 pixels. Each pixel at 100% white is 60 milliamps or 0.06 amps. Now you don't need this column in your spreadsheet, so down at the bottom I say just get rid of it. Column 3 is the percent brightness. In this example I have 100, 50, and 30%. The last column is the maximum current for each string based on the brightness. So the formula for the last column is column A times 0.06 times column C divided by 100. Now the 100 comes from the fact that percent is 1 over 100. For our example, 100 pixels at 100% will draw 6 amps. At 50% they'll draw 3 amps. And at 30%, which is where I run mine, 1.8 amps. So create a spreadsheet and let it do all the calculations for you. Again, if the pixels you have use different components, you may need to change the values to arrive at a closer number. Check the specs. What size wire should you use? These values are for chassis wiring, so 14 gauge wire can carry 15 amps, 12 gauge is 20, and 10 gauge is 30 amps. There are some caveats though. If your wire is longer than about 50 feet, you might want to bump up to the next larger size, but realistically you want to keep them as short as possible. Now, the calculations are based on all white. I haven't seen any display run all white all the time, so your actual current draw will likely be lower than the calculation. But if you do run white, the wiring can handle it. No matter what wire size you use, just make sure you test it. When you build the prop, run all white for a few minutes at whatever brightness you're building for, and see if the wiring starts heating up. Now, if it gets too hot to touch or it catches on fire, turn it off, put out the fire, and make some adjustments. Remember, as you add more pixels to a string, the current draw is going to go up. And even if you're injecting power, you need to make sure that you don't exceed the current handling capability of the wire. Otherwise it heats up or it'll burn up. Now, controller connections are fused, but the power injection connections are not. So you will have to provide your own fuse for the power injection connections. Now, if you're one of those people that, you're saying to yourself, I just don't get this power injection thing, then don't do it. Just stick to shorter strings and you won't have a problem. You will use more controller ports, but you don't have to mess with power injection. You know, potato, potato. Do you need to waterproof the power injection connections? I have only had a problem with power, water getting into something when I had one of these sitting in a puddle of water. Rain has never made the lights go crazy on me, but when this was actually dipped in water for a period of time, the lights started flashing randomly. Not to say that I won't in the future, but I haven't yet. Now I may have a different answer come January, so stay tuned. I am planning to keep the power injection connections for the matrix off the ground, so I've raised it up a little bit, so it's not actually going to be on the ground, so that should keep it okay. It's not going to be in a puddle or anything like that. But if you are running into a problem with water getting into your connectors or your power injection connections, someone suggested using liquid tape or possibly silicone to kind of waterproof those connections. Another question on the last video was, why did you use 5-volt pixels to build this prop? Now, up until now, all of my pixels, except for the 7, I believe, that I have in the Tune 2 sign globe, are all 12-volt pixels. I like big volts, and I cannot lie. But there's actually a couple of reasons for this. First, I just wanted to see how difficult 5-volt pixels were to work with. I'm exercising my power injection chops a little more each year, and it was time to find out what all the fuss was about. It's not that bad, actually. I mentioned this in the last video, but both voltages really have a place in my display. Now, long runs are always going to be 12-volt pixels. They're just easier to deal with. But I might add more 5-volt pixels for props where the power injection is easy to do, like the matrices. The other reason I wanted to do this was just to do a comparison between 5-volt and 12-volt pixels. You know, the 5 volts are supposed to be so much more efficient, and I wanted to find out. I suppose if, once you get up to tens of thousands of pixels, it might be a significant difference in power usage. Now, I'm not there yet, but I did do the comparison. I have the 12-volt matrix that I made last year, and I have the 5-volt matrix that I made this year. Now, both of them have 512 pixels, but I didn't do any power injection on the 12-volt side, so I'm going to limit my test to 50% brightness. And any higher than that, I'm getting close to the fuse limit on the board. With all the props powered on, none of the LEDs on, I got 4.6 watts used by the 5-volt pixels and 22.8 watts used by the 12-volt pixels. Basically, all the chips are powered on, but they're not doing anything. They're ready though. This is measured with my kilowatt meter. I have 110 volt mains, and so we're just doing a comparison on what it says here. So at 30% running all white, meaning all the LEDs are on, red, green, and blue, that makes white. I got 43.7 watts for the 5-volt side and 108 watts for the 12-volt side. That's a little over 2 times. At 50% running all white, I got 67.2 watts for the 5-volt side and 178 watts for the 12-volt side. That's approaching 3 times. So significant enough to be taken seriously. Again, not something I would recommend if this was your first year doing pixels. Just go with 12 volt. They're easier to deal with. You have a whole lot more stuff to learn anyway. Once you get, comfortable with it, then you can move into 5 volt pixels. Final question was about using a really long connection. There's a couple of ways to do it. The easiest is just to use a differential receiver. You've got a controller that supports differential receivers. Standard Ethernet cable comes out of the controller into here. You've got power supply connection here, and then this one has 4 pixel ports for your props. The other solution involves building a special cable. I did a video about this about a year ago, and I'll link that video up here. It was just a longer than normal cable, and it carried both data and power. You could also just build a cable that transferred just the data. But if you do that, make sure you bring a ground along for the ride. The reason for that is if you just bring data, you could have a difference between the controller ground and your power supply ground for the pixels, and so you need that ground wire to make sure that both of the negative sides are the same potential. The matrix is going to be about 30 feet from the controller that I'm planning to use. It's an old F16 V2, and it has a 12 volt power supply for the 12 volt lights around my garage. I could also use that controller to run this matrix by bringing data and ground out of the controller and just connecting ground to the 5 volt supply. And well, here's a diagram. So inline fuse on the positive side of the 5 volt power supply, negative side out of the power supply to the lights, and tie that to the negative side of the 12 volt power supply from the cable that you build. If the cable is longer than about 20 feet, now you can use a single strand of Ethernet cable for the data. Ethernet cable is great for carrying data. So one strand for the data, and then just twist the rest of them together to make your negative side. Don't run any positive through the Ethernet cable. I mean, technically you can, but it will heat up because there's just not enough copper in those skinny little wires. Ethernet cable carries data very well. It handles power very poorly. All right, I hope this helps if you were confused by power injection. It is a little bit of an art form, and you will get better the more you do it. If you'd rather not mess with it, that's okay too. I hope you found some of this information useful. As always, if you have any questions, leave them below. Other than that, thanks for watching, and I'll see you again soon.
Now, I shot an email.
So I got 6 of these, and so I got 5 of these when I started relaxing a little bit, and then BAM!